Alright, this video is going to have the solutions for numbers 61 through 80 in this review packet. We've got a function f with all this information given about it, and also that it's continuous and it's an even function. Remember that an even function, you get the same thing. If you plug in x or negative x, you get the same thing. That causes y-axis symmetry. It's symmetric with respect to the y-axis. Which we're going to need to use because we only have information from 0 to 6 here. Okay, so I'm going to plot here on a separate sheet. Never mind all those dots here. Actually, let me get a... There we go. So the first thing I'm going to do is plot the points that are given. I've got points 0, -2, 2, 0, 4, 2, and that's it. So let's plot those. 0, -2, 2, 0, and 4, 2. And you're like, oh yeah, it's just a straight line. No, it's not, because it's got all these other things going on. So I do know that it does have to have those same points on the other side because it's an even function, and it's got that y-axis symmetry, like if I folded it over that y-axis. Okay, so the derivative here is undefined and the concavity is undefined, so that doesn't really help me much. I do know that the function is negative from -2 to 0. Well, that makes sense. It just means it stays in negative territory. That doesn't really help me draw it at all. I know that the slope is positive. Okay, that makes sense. And I know that the concavity is negative. It's concave down. So that means it must be going like this. And I also know that the slope is 1 here. No, that's actually impossible. That's funny. We'll pretend that that's possible. That slope would have to be a little bit less than 1 for it to be concave down. If you really want to know like why that's technically impossible, you can ask me about that. It has to do with the average slope being 1 here. If it's concave up, it has to be concave down rather. It has to do that. It would have to have lower than 1 slope there. So, oops. And then at the point 2, goes through that point, it has a slope of 1, and the second derivative is 0, and it's changing from negative to the second derivative is changing from negative to positive. That's an inflection point. So that's going to go like that, and now I have positive function values. That just means above the x-axis it's increasing because the first derivative is positive, and it's concave up because the second derivative is positive. So that means it's going to look like this. And then when I get here at 4, the first and second derivatives are undefined. The first derivative is going from positive to negative. It's going from increasing to decreasing, and it's staying concave up. So it's going from increasing to decreasing, but staying concave up. So maybe it looks like that. And that would explain why that those first and second derivatives are undefined there. So to make it the full even function, just going to trace out the rest of those bits. Got to be symmetric there. Looks kind of like a fox. Okay, with little ears and little whiskers there and whatever. Alright, so that's that. Oh, except I have some more parts here. So identify all x coordinates at which x attains local extrema, and classify them as minimums or maximums. So I've got minimum at x equals 0 because the derivative goes from negative to positive. and I have maximums at -4 and 4 because f prime goes from positive to negative. Identify all x coordinates of the points of inflection. That happens at here and here. Because the second derivative changes sign. And then there's my graph that I sketched. I did C first. Alright, that was fun. '62. Implicit differentiation. So implicit differentiation is when the x's and the y's are kind of mixed together here, and we just plow through and take the derivative. So derivative of x squared is 2x, and the derivative of xy, that's a product, is the derivative of the first times the second plus the first times the derivative of the second equals 0. So we want to know what's dy dx. We could solve for dy dx. Move those things to the other side. Dy dx would be equal to minus y minus 2x all over x. That's moving those two over to the other side and then dividing by x. And when x is 2, what's dy dx? Well, I'd need to know the y value also, so I need to go back to here to find that. So here, 4 plus 2y equals 10. That's plugging x equals 2 in here to find the y value, which would be 3. So then I plug in 2 for x and 3 for y into this. So minus 3 one way of writing that, so dy dx at the point 2, 3. So minus 3 minus 4 is minus 7 divided by 2. Alright. Find y equals f of x by solving the differential equation here with the initial condition. This is recent for us. This is from chapter 9. So separate the variables. It's going to be 1 over y dy equals 2x dx, and anti-differentiate both sides. That gives me natural log y is equal to x squared plus c. Raising e to the both sides gives me y equals e to the x squared plus c. I'm going to move that c out to the front because we can do that. And then the initial condition, when I plug 0 in for x, I get 2. So 2 is equal to c times e to the 0. C is equal to 2, because e to the 0 is 1. And then my final answer is y equals 2 e to the x squared. All right. Consider this differential equation here. Sketch a slope field for the given differential equation at the 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's 16, not 12. What the heck? So for those 16 points, so this differential equation, the slope is just whatever the x-coordinate is minus 1. So when the x-coordinate is 1, I get 0. When the x-coordinate is 2, I get 1, -1, -2, like that. Sketch a solution curve through the point 1, 0. Now that would go up like this over here, and up like this over here. It's like a parabola. And sure enough, we're going to find when we solve it here, antiderivative of just looks like a 1 is just y equals x squared over 2 minus x plus c. Initial condition f of 1 equals 0. When I plug 1 in, I get 0. So it looks like c is going to be 1/2. There you go. And just to make connections here, what we just did is we actually found the curve that we sketched here. This is that parabola. All right. Remember your plus c. All right, so this is the same as 5x to the negative third. And that's just easy reverse power rule. So add 1 to the exponent and divide by the new exponent. You can put that negative sign up top, like out front, if you want. This is, it's likely that you'll see maybe just one time a problem like this where there's just a monomial on the bottom and you just have to divide through by that to simplify. So I'm going to do that. That's the same as x cubed over x squared is x minus 3, and then x over x squared is plus x to the negative 1. Antiderivative of that is x squared over 2 minus 3x. Antiderivative of that, bump the exponent up 1. Oh, wait a minute, it's 1 over x. The antiderivative of that is natural log x. Here, it looks like I'm going to do a u substitution, right? When you have like an inside thing and then there's another little x sticking around there. So if I made my u equal to x squared plus 5, then du is equal to 2x dx. Need a 2 here, 1/2 on the outside. But that turns into, like, the 2x dx turns into the du. And square root of u, I'm going to write it as u to the 1/2. I'm going to bump the exponent up by 1. That's 3/2. And divide by the new exponent. Same as multiplying by the reciprocal. 1/2 times 2/3 is 1/3. And u is equal to x squared plus 5 to the 3/2 plus c. Antiderivative of cosine is sine. Here, looks like that wants to be the u. So du is equal to 27 x squared dx. So I need a 27 on the inside. I've already got a 9 there, so if I just multiply by 3 here, that'll turn that into a 27. And 1/3 on the outside. Okay, so this all cleans up into secant squared u. Excuse me. Antiderivative of secant squared is tangent. That's a thing you need to know. And third tangent, u is equal to 3x squared, 3x cubed rather. Here, looks like my u is going to be that cotangent x. Du, the derivative of cotangent is interesting. The derivative of cotangent is negative cosecant squared, not cosecant cotangent. So, either this is a badly written problem, and that should be cosecant there, or we got to come up with something else. I don't know if there's another way to do it. Let's see. My guess is that it's a badly written problem, and you know what I'm going to do just for practice? I'm going to pretend that that was cosecant x, because that's what it looks like it's trying to match up to. So the derivative of cosecant x is negative cosecant x cotangent x. So I would need a negative sign inside and outside to turn it into e to the u du. I think that's the intention of the person who wrote that question. It wasn't me. So how about Riemann sums? Bunch of rectangles. Use a right-hand Riemann sum with 4 equal subdivisions to estimate this integral here. So 4 equal subdivisions, it's going to be 0 to 2. 0 to 2 is the whole thing, so that means my rectangles are going to be 0.5 wide. And I'm going to get the different values. Since we're doing a right-hand Riemann sum, that means the values that I plug into this are going to be 1/2, 1, 1.5, and 2. Right? Those are the right endpoints. If you imagine, this is 0, 1, 2, half. So the right endpoint of the first one, that's 1/2, and then x equals 1, then x equals 1.5, and x equals 2. So if I plug 1/2 into this, I get negative 1/4 plus 1. If I plug 1 into this, I get 1. If I plug 1.5 into this, I get negative, let's see, that's 3/2, so negative 9/4 plus 3. That's 0.75, I think. I think that's right. And then, I'm sure you'll let me know if it's not. Plug in the 2, I get 0. So I think that that all adds up to 2. Maybe? Let's see. This is half of a 3/4, and half of a 3/4 is a 3/4. 3/4 plus a half is 1.25. I think that that's right. And you can check that. Check my math. Use a left-hand Riemann sum with 4. Okay, so let's set it up exactly the same way. And I'm going to try not to redo work that I've already done. So now I'm going to be plugging in 0, 1/2, 1, and 1.5, and not using that because these are the left endpoints. When I plug in 0, I get 0. When I plug in 1/2, I get that. When I plug in 1, I get that. When I plug in 3/2, I get that. So it looks like it's actually the same thing, right? That kind of just shifted over. That's sort of lucky. That's not typical that a left and right Riemann sum on the same interval are going to be equal. Use a midpoint Riemann sum with 4 equal subdivisions to, okay, this is a different one now. I might just make a quick sketch of that. This is the absolute value of x minus 2. That's like the absolute value function, shifted 2 units to the right. So midpoint Riemann sum with 4 equal subintervals. So that's here. So each rectangle is 1 wide, and the first one is going to be 3/2 high, and the next one, the midpoint height is 1/2, and then 1/2 and 3/2. So 1/2 and 1/2, a whole, and that's so 4, I believe is what we get there. Riemann sum means rectangles. So how about a trapezoidal sum with 3 subdivisions of lengths 2, 3, and 1 to estimate that? Okay, so if I have the interval from 0 to 6, and the widths of my rectangles are 2, 3, and 1, then the things I'm going to be plugging in are, like, those are like the little edges of the trapezoids. So, to find the area of a trapezoid, I do how wide is it divided by 2, and then I add together what I get when I plug in the 2 boundary values. So when I plug 0 in, I get 0. When I plug 2 in, I get -4 plus 12 is 8. The next trapezoid is 3 wide. When I plug in 2, I get 8. When I plug in 5, I get -10 plus 30, -25 plus 30 is 5. Right? That looks good. And then the last trapezoid is 1 wide. And when I plug in 5, I get 5, and when I plug in 6, I get 0. Okay, so I got 1 times 8, I got 3/2 times 13, and I got 5/2. That's 44/2, or 22 plus 8 is 30. Looks like I'm getting 30 for that. Hope that's right. Alright, fundamental theorem. I'm going to finish up these last few problems in just 1 sec. Back. I'm back. So this is the fundamental theorem, part 1. Sometimes it's written like this. If this thing on the inside is already derivative, then we get back up to the level of original function. And this should be qualified by saying where f prime of x is equal to f of x. In other words, this is an antiderivative of that. All right. So we know how to do these. These are easy. Antiderivative of this is x cubed over 3 minus 4x, and then do my little brackets like that. Plug 3 in here. That's 27 over 3 is 9 minus 12. And when I plug -1 in here, I get -1/3 plus 4. Got to be careful with your negative signs. That looks like -3 minus 4/3 minus 1/3, so 11/3, I think. And that itself, that's -9/3 minus 11/3 is -20/3. I think that's what I'm getting there. And then I'm going to do that again here. Notice that these are going the wrong way, but it doesn't matter if I just follow the directions, follow the recipe. You could switch them and pop a negative sign out. It's an option. Antiderivative here is x squared minus x from 3 to negative 2. So looking in the negative 2 first, I get 4 minus negative 2 is 6. When I plug in 3, I get 9 minus 3 is 6. So you get 0. Just double checking that. Yeah, that's a that's a badly written problem, because if you made the mistake of the order of this, it wouldn't matter because you just get negative, you get the 6s the other way around. So make sure that you're doing that the right way around. Find the value of x and k that divides the area between the x-axis, x equals 4, and this into two regions of equal area. Okay, let's see what I can do there. What does that look like? I'm going to make a little sketch. That x equals 4 is that line. And find the value of x and k So I think this is kind of not quite clearly written here. This should be, it should be find the value of k such that the line x equals k divides this into two equal areas. That's what it should say. Sorry about the lack of clarity there. So what I'm going to do, I'm going to find this area, and then I'm going to cut that in half and set up an integral and try to solve that. So the first thing I'm going to do is find the area from 0 to 4 underneath the square root function. Bump that up and divide by the new exponent from 0 to 4. And for the 3 halves power 4, that's the square root of 4 is 2, cubed is 8. Times that is 16 thirds. I plug 0 and I get 0. So that's the area of this. So half of that area, I want to divide this into area 8 thirds, 8 thirds. That means I want the integral from 0 to k of square root of x, or, sorry, if you write that as x to the 1/2, I want that to be equal to 8 thirds. Half, right? Well, I already have the antiderivative. It's this. So I want this 2 thirds x to the 3 halves from 0 to k to be equal to 8 thirds. So I have some math to do here. When I plug in the 0, I get 0. So when I plug in the k, I get that 2 thirds x to the 3 halves, k to the 3 halves, so I plugged in the k here, needs to be equal to 8 thirds. So k to the 3 halves must be equal to 4, so k must be equal to 4 to the 2 thirds. That's my final answer. All right. Properties of definite integrals. Last couple problems on this page. Let's see. So if this is equal to 10, then what's the area of this plus 4? Well, you can split up integrals like this. And this is equal to 10, and this is equal to 12. Do you know why? You could take the antiderivative and say, okay, that's 4x, and you can do some plugging in, and you could find it that way, 20 minus 8. But it's also like, this is just a constant function right here, 4. That's horizontal line at 4. And if you take the area under a horizontal line from 2 to 5, that makes a rectangle that's 4 high and 3 wide. So either way, you get 10 plus 12 is equal to 22. A constant like that, you can move to the outside. And if that's true, I know this is 10, so that must just be equal to 70. And then here, that shifts it. So you could do a u substitution is one way to think about this. So du is equal to dx. No change there. So the difference is when you put the u in here, it now changes these numbers to 0 plus 2 is 2, and 5. And good thing it changed it to those, because that's the only thing I know how to find the area for. What they did not include here is when you have like this and then another interval that has like 2 to 7, and you have to like subtract the intervals from each other. That's something that you're very likely to see somewhere along the way. I'll make sure you see that in practice somewhere. Okay, so the mean value theorem for integrals, we didn't really call this, but it's just that the average height of a function has to be attained somewhere by the function. So the average value of a function is not something that's included as part of the BC curriculum. I could show you how to do it. It's just this. So you can try that if you want. But that's not going to show up on other assessments and practice things that I give you. And so I'm going to cross that one out. If you did that one and you want to know what the answer is, just come ask me, I'll show you. Or if you're more curious about that. On the other hand, average velocity really is something that we want to know how to do. Oh no, given this, never mind. If they ask us average velocity, we're going to be given a position function, and we're going to just find the slope of that. So I'm going to X that one also. So there you go.